Hi, everybody. I originally recorded the screenshot that you see right now that is recording or that is playing is the one I recorded, but I really wasn't recording. I was hoping that I was doing it right. This is going to be interesting because me talking right now isn't going to match up with it's going to be like one of those old movies, like martial art movies. Hilarious. All right, I need to like get on task. Sam Cavender, come on, you need to be here. Tell me this. Anyways, water resource facts. I talked about how there's lots of water resources. Um, uh, there's not a lot of resources. 97% of Earth's water resources are in the oceans. We can't use it. 2% are locked up in polar ice caps and in groundwater. We can't get to it. And the remaining 1% is what we have in surface water, in lakes, rivers, ponds, and so on, and the atmosphere. So this 1%, what I'm saying right here, in the original recording that didn't have sound, and I didn't know it, is the fact that if we had like a 10-gallon bucket and we put 1 drop of water in the bucket, that would be like an analogy, an example of how much water we actually have available for us to use for industry, human consumption, industrial processes, agriculture, all of that. So it's not a lot. So in this slide, I was referencing the fact that we need to really take care of it. Um, Not only is it about us, but it's about other organisms too. So we also have plants, animals, microbes, and other aquatic organisms that actually depend on this 1% along with us. Um, so more than 99% of the Earth's water is unavailable. It is unsuitable. We can't get to it, and it's because of salinity. It's just we don't have the infrastructure to desalinize it, and it's also because of location. There is technology for desalination. We'll get into that later. So where does our water come from? Most of it actually comes from aquifers, and aquifers are basically underground water wells that are naturally occurring. Um, and the underground water wells are referred to as aquifers. It's made up of soil or rock, and there's cracks and fissures and spaces between it within which the water resides. So it's kind of like a holding tank of water. We do need to know that water moves really slow through aquifers, so it doesn't just sit still. But we're talking, centimeters to meters a day. It just depends on where it is. Aquifers have to be recharged. If we take water out of them, then what you leave behind is empty space. And less water. So here I am about to draw an image of an aquifer, a very simplified image, which will soon be connected to another aquifer. And what I'm doing here is I'm trying to show you how the water from one can move to another. And so as the um, water moves from one place to another place, it's moving very slow. And keep in mind that around here could be possibly a hazardous waste dump where there's like barrels underground and they're leaking, and that the the pollution then gets into the groundwater and that causes issues. Um, and it's very, very costly to clean up. Here now I am talking about the surface, the part above the aquifer, like on the surface. Because of development, we have more and more impermeable surface, which is illustrated here in black. And then the green part is permeable surface. And that permeable surface allows for the recharge of these aquifers, and that water will percolate down and refill those aquifers as we use them. Um, but again, like I said before, there's less and less of that available. So as a result, we need to improve and enhance and create more permeable surface. Um, so um, we want to increase permeable surface. Yes, that's what I meant by that arrow. And by doing that, we could allow for water to infiltrate through. I think here I'm about to talk about turf grass and how shallow the root systems are, and how it technically is kind of like impermeable surface, because um, when precipitation occurs and hits that turf grass, it can't really um, get absorbed down into the ground, it just runs off. Okay. Um, so what you should be doing for this flip is not only writing down what I've underlined, but also these illustrations. I'm going to be looking for these illustrations and little notes on what I'm saying about them in your notes. This red part here that I just drew is actually supposed to be like a rain garden. I was providing an example of how we can enhance or improve the quality of the permeable surfaces that we do have on the earth. And we're going to be doing that. You know, there's the rain garden group that we have in the class that is going to be making a rain garden. And so rain gardens have deep root systems, which is illustrated by those long red squiggly lines. And so as that water goes down, it'll actually, those roots will draw that water down and pull it down into the aquifer to recharge it. There we go. A little behind there. Um, so that's called percolation, okay, when that water gets pulled down to restore. The area that's permeable, again, is called a recharge area, okay? Um, and there we go, percolates. So I'm a little ahead of myself. And the next slide, I'm actually going to talk about two different kinds of aquifers. There's aquifers that are actually exposed at the surface, and then there's aquifers that are underground and we can't see them. The kind that are exposed at the surface are referred to as superficial or unconfined aquifers. So there is an entrance to the aquifer at the surface. A lot of times there will be water seeps or springs of water that are always at the surface. And some rivers are actually, and creeks and feeder streams are essentially exposed water table or exposed aquifer at the surface, and it creates the watershed. It contributes, so the water from it contributes to the volume of water that we have in those watersheds. Um, Superficial or unconfined are much more vulnerable to our everyday activities simply because of their location. When we look at confined aquifers are underground, obviously. They are harder to monitor because they are underground, so you have to drill wells in to have monitoring um, parts there. And the reason why it's confined is because of the geology. A confined aquifer is one that actually kind of has like a clay cap or an impermeable cap of rock. And this impermeable cap of rock could be made of shale or slate. And in this slide here, I put clay, shale, slate. Clay, we all know, is very impermeable. That water can pass through clay, but it's very slow. Um, and then when clay succumbs to pressure, it can become a rock. And when clay is under lots of pressure, we're talking over millions of years, it can become shale. And then shale actually can become another type of rock if it is exposed to heat and pressure. And it metamorphoses into slate. Okay, so kind of like the life cycle of a rock, and we'll be learning about this next week in chapter 10. A perfect example is clay, which is a sediment, which becomes shale, which is a sedimentary rock, and then slate, which is metamorphic. Okay? And what that does is it leaves an impermeable surface, so it keeps it confined. This is an illustration of an unconfined aquifer showing the spring right there that's exposed at the surface. You know, the spring in this picture is kind of funny because not all springs like are fountains. They really are just wet areas in um, forests and stuff. Um, so, or anywhere really. And so that is an entryway into the unconfined aquifer. It is exposed to all of the elements with regards to how we use our land, and so they are much more vulnerable to pollution. Whereas confined aquifers, which is the one to the right, you could see that there's a confining cover. That confining cover again is made of an impermeable kind of rock that does not allow for that water to be um, exposed. And so as a result, these water wells have to be drilled. And these water wells not only are drilled to get to the water, but also for monitoring. And if you look at this, it also has this term called cone of depression. You see as the aquifer level water table lowers, what happens is there's an area right around the injection site where it pulls the water out. It's called a cone of depression. And so that is an area that where there's no water. And so that area can be susceptible to pollutants moving to it. And that could create problems with water withdrawals and water being contaminated. Um, and I think that's it. Um, so Yeah, I think that's it. So sorry about the whole recording thing, but I think you got the gist of it. Okay? And that's it.